For our second example in quantum communication, we now turn to quantum teleportation. We will start by stating the purpose and then develop the quantum circuit around this, and on the way we will make sure that this really works. Well, the purpose of quantum teleportation is to start out with a single qubit in a certain state psi. And this can be a completely arbitrary state, so this state is completely unspecified. And what we want to achieve is to transfer this state onto another qubit. So this other qubit at the end should end up in the same state, but this other qubit is located at a distinct location, somewhere away from the first qubit. And the way that we are going to achieve this is to make use of a third qubit that is initially entangled with the qubit that we want to transfer this state to. So we start out with a maximally entangled state between these two qubits, for which we simply make use of our simple Bell pair. But this additional qubit, we assume, is within the realm, within the range of influence of our original qubit. So you can think of this again as a quantum process carried out between Alice and Bob, who cooperated in the distant past to obtain access to this maximally entangled Bell pair here, but then went their separate ways, and all of this might have happened well before Alice even got access to this quantum bit here. The key idea is to somehow transfer the quantum correlations in the entanglement of these two quantum bits into quantum correlations between this quantum bit and this quantum bit, so that at the end we obtain this quantum state here. And the way that we can achieve this is to make use of our disentangler circuit, so the inverse of our entangler circuit. In there we have again this controlled NOT operation, and then a Hadamard gate. So this is really a key component in this quantum teleportation circuit. This just operates on the first two quantum bits, and let us see what we can achieve in this way. Let us work out how the quantum state of this complete quantum system looks like at this stage, which I enumerate as 1. This will be the quantum state of the whole system, so the state of these three quantum bits at this particular point. Well, we need to start with the initial state, and this is the state psi for our first qubit, and the Bell pair beta naught naught for the other two qubits. And the first qubit we are generally going to write as this superposition here, just with arbitrary coefficients alpha and beta. And the Bell pair is just of our very familiar form as given here. Let us multiply out all the terms so that we can really write this as computational basis states of the 3-qubit system. So then we, for instance, have the amplitude alpha divided by square root of 2 for the state in which all the 3 quantum bits are in the state 0. And then we have similar terms such as this one here, where the first quantum bit is 0 and the other two are in the state 1. And we can just multiply out also all these terms here. So we get 4 of the 8 possible computational basis states at this point. Let me call this initial state simply phi. So this is the initial state of the 3-qubit quantum system. Right, next we need to apply the controlled NOT gate onto this state. And this is a controlled NOT gate where the first quantum bit is controlling what happens to the second quantum bit. So the first quantum bit are these entries here. And whenever these are 1, we need to do something to the second quantum bit, which is in these two cases here. So what we find is that nothing happens to the first two components in this superposition. So we can just copy these down. But in the second and third component, the second quantum bit changes its state from 0 to 1 or 1 to 0. So this is the state after the controlled NOT operation, and I'm going to denote it as phi prime. Next we apply the Hadamard gate to the first quantum bit in this state. And this will now generate a superposition of all the computational basis states with very specific coefficients that we obtain when we just apply the Hadamard gate to this first quantum bit. And here we are just going to use the rule that in these two cases we will obtain the even superposition of the states 0 and 1 for this quantum bit, and in these two cases we obtain the odd superposition. There's always a factor of 1 over root 2 involved in this. So we, for instance, obtain these two states here just from the even superposition. And here we obtain similar states from the odd superpositions. So let us call this state then phi 1, because this is really the state at the stage 1 which I indicated in the circuit. Well, this is a relatively complicated quantum state of the complete system, making use of all the computational basis states, but it actually has a very simple structure, and this we can identify by separating it into the pieces which are in possession of Alice and Bob. Alice is in possession of the first two quantum bits, and if these are, for instance, in the state 0, 0, then we can read off that Bob's quantum bit is really in the state as given here, where we simply pull this factor 1/2 to the very front. Well, this factor 1/2 appears in all of the expressions, so let us factor it out completely. And then let's continue to see what happens if Alice's qubits are actually in the state 0, 1. Well, this corresponds to these two cases here. And then Bob's qubit has a beta in front of the 0 and an alpha in front of the 1. So we can write this in the following form. Now we just continue to the next combination of Alice's quantum bits, which we find realized here and here. And in that case, Bob's quantum bit is in this state here. And finally, when Alice's quantum bits are in the state 1, 1, we find this realized here. Then Bob's quantum bit is in this state here. And now we see that there's a very distinct correlation between the state of Alice's quantum bits and the state of Bob's quantum bit. And in all cases, the state of Bob's quantum bit involves the coefficients alpha beta that we had originally in our state psi. So what would be really nice if we would have a mechanism by which we could find out in which state Alice's quantum bits are. Are they in this state, or this state, or this state, or this state? Because then we would also know in which state Bob's quantum bit is, namely this state here, this state here, this state here, and this state here. And we can of course figure this out by simply doing a measurement. So all that we need to do now is to measure the quantum bits in Alice's possession. So these two quantum bits here. And we are going to call the result simply M1 and M2. And by these double lines I indicate again that we have now converted this into classical information. So let us have a look at the effect of this measurement on this quantum state here. Well, according to the measurement postulate, the quantum state will be changed into a new state, which depends on the measurement outcomes M1 and M2. Well, we can collect this into a table where we list all the possible measurement outcomes here. And the final state after the measurement on this side here. So these are the 4 possible measurement outcomes, and they simply correspond to these 4 different states here. Well, all of these states are indeed normalized, and they're all multiplied by this factor 1/2 here. So first of all, we recognize that all these measurement outcomes occur with the same probability 1/4. And then the measurement is also forcing the quantum system into the corresponding state, depending on the measurement outcome. And as these all separate into a piece for Alice and Bob, I'm going to list them separately here. So for the case that the outcomes are 0, 0, Bob's state is this state here. For 0, 1, Bob's quantum bit is in this state, while for the outcome 1, 0, we have this combination here, and for 1, 1, we have this state here. And when we look at this, we see that this state here is indeed just the same as the state psi, the original state of the first quantum bit. And it does not end there. All the other states are actually related to psi in a very systematic way. For instance, this state is obtained from psi by applying a Pauli X gate, so a NOT operation. This one here is obtained by applying the Pauli Z gate on this single quantum bit. And this one here is obtained by applying first a Z and then an X operation. And this now means that Bob can reconstruct the quantum state psi in all cases when he knows the values of these classical bits here. So all that Alice needs to do is to transmit these classical bits to Bob. So at this stage, only classical information is being transmitted from Alice to Bob. So all that is required, that is classical information, is being sent from one person to the other. And what Bob then needs to do is to implement operations that revert the relation between the state that he has obtained and the state that he desires to have, namely the state psi. And these are simply classically controlled gates, controlled by these values M1 and M2. Namely a Pauli X gate and a Pauli Z gate. Well, let us briefly check that this indeed works. So for the case that the 2 classical bits are 0, the 2 gates are not applied, and then indeed we already have the state psi here. When the second bit is 1, we apply the X gate, and this indeed reverses us back to the state psi from this state here. And the same happens from this state here when we apply the Z gate. And in this case here, we indeed need to first apply an X gate to cancel out this term, and then apply a Z gate to obtain the desired state. So what we have achieved is that Bob is now in the possession of a quantum bit in the state psi, which coincides with the original state of the first quantum bit. And this is really the purpose of quantum teleportation. And what is remarkable about it is that this was an originally completely independent state, which never interacted in a quantum way with this third quantum bit here. Of course, we had some initial entanglement between these 2 quantum bits, but we managed to transfer this to the first quantum bit. So we created some quantum correlations between all the quantum bits, including the first quantum bit. And then we could obtain some knowledge about these correlations by simply doing a measurement, and only transmitted this information classically to Bob. which he could then utilize to reconstruct this state here. Let me add some further remarks. First of all, it is important to emphasize that this does not correspond to copying or duplicating this state psi. At no point any of the other two quantum bits are in the state psi as well. In particular, after the measurements, the two remaining quantum bits are forced into computational basis states. So we cannot get around the no cloning theorem by this mechanism here. Secondly, in this realization of the quantum teleportation circuit, we made use of the specific Bell pair beta naught naught here. And it is indeed instructive to see what happens when we make use of any of the other Bell pairs. So for instance, what happens when we start out from the Bell pair beta naught 1. Well, this is related to beta naught naught by applying a Pauli X gate, a NOT gate, to any of the two quantum bits. For instance, to what is now here really the third quantum bit. But we can then simply relate this to the circuit that we just discussed by inserting a Pauli X gate here, because then at this stage we just revert back to our state beta naught naught. And we can place this here at any point along this line, for instance just in here. And now the combination of this X gate here and the classically controlled X gate that just follows, which is controlled by M2, is just the same as just applying this classically controlled X gate, but always when M2 is actually 0 and not 1. So Bob can simply apply this quantum gate before he applies these gates, or he could simply replace this classically controlled gate by this classically controlled gate. And you can do this, of course, also for the other two Bell pairs, and in all cases you just need very simple modifications of this original circuit. But what you need to make sure of is that you indeed know which of the different Bell pairs you had at the very beginning. Because if you do not know this, you also don't know which of the reconstructing operations you need to carry out at the very end. And this can also be seen in another very instructive way. Because if you don't know which of the Bell pairs you have, well, then you have four choices. You would say each of them occurs with a probability 1/4. Then you really deal with this density matrix here. So here we just sum over all possible Bell pairs. And this now turns out to be just the same as 1/4 times the identity operator or matrix. And you can see this in different ways. And what I suggest that you do is to just insert the definitions of the Bell pairs here. Because when you multiply this out, you see how all the different terms cancel, and this is really instructive. But another way to see this very directly is to see that all the Bell pairs indeed are orthogonal to each other, and they are also normalized. So they indeed form a complete basis because there are also 4 of them. So they cover the complete Hilbert space of 2 quantum bits. So therefore what we have here is just the standard resolution of the identity. And so we obtain this one directly here. And why is this instructive? Well, you can write the identity in many different ways, including as a resolution of the identity simply in the computational basis. So these are now not Bell pairs, but these are the computational basis states. But none of these are, of course, entangled. These are all separable states. So this means that there is no physically detectable difference between a situation where you are in one of the Bell pairs, but you do not know which Bell pair it is, and a situation where you are in one of the computational basis states, but again, you don't know which of them it is. And because in this situation here, you do not have any usable entanglement, you do not have any usable entanglement in this case as well. So if you're in this situation where you have bell pairs, but you do not know which bell pair you are in, then you have no usable entanglement whatsoever. And this is indeed the reason why I sometimes emphasize that dealing with entanglement is quite easy when you have pure states, but it becomes quite a bit more complicated when you deal with mixed states. Okay, so this concludes our discussion of quantum teleportation. The quantum teleportation circuit is really beautiful and neat, and again makes clever use of entanglement to again transfer quantum information from one location to another. Now we turn to our final class of applications in quantum communication, a very rich area in itself, namely quantum key distribution.